So we're going to use heuristics to understand things now. The next antenna I like to describe to you is the horn antenna. It's a flared horn. You can see that the horns are flared. So why do we need to flare the horn? It is quite easy to understand from the concept of impedance matching. Say if you have two transmission lines connected, such as this one over on the right-hand side, you want to match Z0 to Z1. You have to put a matching network in between. And in order for this matching network to work, so that there's no reflection as the wave comes in here, you pick Zm to be the square root of Z0 times Z1. I think you did this as a take-home exam. So which means that if you pick this Zm, which is some geometric means of Z0 and Z1, there's a name for this mean. I think it's called geometric means. Okay, so we know that the wave impedance of free space is about 377 ohms. Okay, you have something like 377 ohms on one side. And then here you will have waveguide microwave engineering. Usually we work around 50 ohms in microwave engineering. So in order to match the two impedances, you will put something in between that is intermediate between the two impedances. You gradually change the impedance so that the wave can travel comfortably from this end to the other end without suffering reflection, just like over here. Here is very simple because we only have one section and it only operates at one frequency, okay? But here you might want to operate this antenna over a wider band of frequencies, and hence you flare it gradually. And these are different designs of horn antennas. And here is the corrugated horn antenna. We call this the corrugated horn. Okay, we call this the corrugated horn. The reason why it's corrugated is because you probably learned from your waveguide theory section that if you have corrugations in a circular waveguide, it enhances the TE10 mode. The TE10 mode is axially symmetric. And when you have an axially symmetric mode propagating out there, then the radiation pattern is also axially symmetric. That's why we want to enhance this TE10 mode of the horn antenna so as to arrive at the radiation pattern that is circularly or cylindrically symmetric. Okay. Yeah, sorry, it's a TE01 mode, not the TE10 mode. It's TE01 mode. So if you excite the TE01 mode in the circular waveguide, that mode is axially symmetric, and that mode can be enhanced or excited by having corrugation that encourages circumferential current flow, but not axial current flow. And it will try to mitigate the other modes. Okay, so this is the corrugated horn antenna, and let's go to other kinds of clever designs that people have come up with using heuristics. And another antenna that people have come up with is called a Vivaldi antenna. Vivaldi antenna is invented by Paul Gibson. It was not invented by the musician Vivaldi. He just likes these musicians so much that he names this antenna after Vivaldi. Okay, I believe it's invented around the 1960s. So you can think of a bicone antenna or the flare antenna that we talked about before, that if you flare a transmission line, you can allow for the matching of the impedance of microwave engineering, which is usually around 50 ohms, to that of free space, which is around 377 ohms. So if you have something like a notch antenna, usually this notch is actually spelled with the ED at the end, okay, flat horn antenna, you can see that the impedance is gradually been matched from the microwave engineering side to the free space side by using this flare horn. And the flare horn is good because it uses a very little metal. Unlike the other horn antennas that you have to do quite a bit of plumbing and actually make this thing massive so that they're heavy, but the flare antenna can be made out of a very thin metal plate. Another good thing about the flare horn antenna is that it actually gradually flares. It becomes wider and wider, which means that when the high frequency wave is leaving this antenna, they ride on this part of this horn because their wavelengths are very short. However, the longer wavelengths that leaves the source will have to ride on this part of the horn antenna because the gap here is bigger. So the horn antenna is also broadband in the sense that it allows wavelengths of different sizes to emerge from this antenna in a very comfortable fashion so that you can get radiation over a broader bandwidth. Okay, so are there any questions so far?